Good. So this is Physics 7, February 23rd, 9:42. And let's continue with the material we started. We have been covering, right? So here you go. Now let's share the screen. This, okay, this is, okay, here you go. 23rd, let's take a look at the syllabus, just to locate where we are. We are writing here, 23rd of February. And we will continue with the electric field, and hopefully we're going to get into the electric potential. Okay, electric potential here. And then when we finish the electric potential, we'll be ready to discuss the lab number 1. Because the lab number 1 makes use of the concept of the electric potential. And let's take a look also at the chapters in the book. Here you go, here are my notes. All right. And so you can locate the first section in chapter 18 is the origin of electricity. Okay, electricity has been known for thousands of years already in ancient Greece and even the civilizations of the Middle East, the ancient civilization of the Middle East. They knew about that static electricity effect, especially the Jewish people, right? The Jewish people, some of the Jewish people were those Bedouins of the desert, and they wouldn't stay in a single place. They would move around in that region of the Middle East through the desert and camels, and they were nomad people. But they, just because they are nomad people doesn't mean that they were poor people. No, they are not poor people. They are very wealthy people because they would trade with the other civilizations in the region, with the Egyptians, with the Babylonians, even the Sumerians. And as they walked through the desert, they noticed that they would be subjected to that effect that we know very well of static electricity, right? Especially in the climate of the desert that is very dry and allows for us to be electrically charged more easily. So the origin of electricity dates back to this time. Okay, and that's what this chapter is all about. The next one, charged objects and electric force. Charged objects and the electric force. Okay, we covered that, charged objects. And we also covered the electric force. 18.3, I mentioned about conductors and insulators. The best conductor there is silver. The second best conductor is copper. 18.4, is charging by contact and by induction. I didn't mention that, so let's just skip it for now. It's possible to charge objects just by just getting, let's see, charging by contact, right? It's possible to charge just by rubbing one object against another one. I didn't mention that, but I want you to keep that in mind. Okay, when I was a kid in elementary school in Brazil, we used to play with with pens. Okay, here you go. Here's my pen, right? My pen. And what we discovered, no, we like to play with that, and most likely you folks also did that, right? If you rub it against your scalp and would place small pieces of paper next to the pen that had been rubbed against the scalp, you'd be able to attract these pieces of paper. Okay, so it's possible. One way to charge an object is by rubbing it against another one. That's one way. Another way is just by getting a battery, connect your object to the poles of the battery. The battery is electrically charged at different terminals. There's the positive and the negative terminal of the battery. And those charges from the battery will be transferred to the object. That would be another one, another way of electrically charging an object. So it's important to cover that, not because it's going to show up in the exam, okay? It's important to cover that because you must have an idea of how we can electrically charge an object in real life. Okay, so those are at least two different ways that you can do that. By rubbing one object against the other and by connecting your object to, for instance, a battery, one of the polarities of the battery. The battery has two polarities, one positive and the other negative, right? The polarities positive and negative means that you have an accumulation of positive charges in one end of the battery and accumulation of negative charges of the battery on the other end. Let me get one battery so you can see here. In case you never know, see that? Here you go. In case you never know, here's a AAA battery that I have. Let me stop. Oh yeah, here you go. I'm going to stop sharing my screen, okay? And then remind me to share the screen back again if I forget to do that, okay? Let's see how I'm gonna stop sharing so you can see my battery right in here. Okay, that's a AAA battery. Okay, if you analyze any battery, if you analyze closely, you're going to see that it has a positive sign at the tip that sticks out from the battery. And okay, what does it mean, a positive sign? It means that this tip of the battery is positively charged. We have a separation of charges in the battery. Here at the end at the top is positively charged, and at the bottom is negatively charged. They did put a negative charge symbol here at the other side of the battery, okay? So one way to charge an object would be to connect this object to one of the polarities of your battery. Every battery is like that. That's a AAA cell. And let's go back to share the screen. Next one, Coulomb's law. We covered Coulomb's law, right? Coulomb's law, Coulomb's force law is our first law of electricity. And then we start covering the electric field. The electric field. And we also have the Coulomb's law in another format. I'm going to put like that. Here you go. Here would be Coulomb's force law. The book didn't spell out this way, but I want to make a distinction between this section and the other one, right? Coulomb's force law. And here we are going to have Coulomb's force electric field. We are going to have Coulomb's force law, Coulomb's not force law, but Coulomb's electric field law. I mentioned that to you before, right? that the electric field of a point charge is also referred as the Coulomb's law, but should be the Coulomb's law in the format of the electric field. We covered that. 18.7. For now, we're going to the electric field inside a conductor. We're going to skip that for now. And the final, oops. I'm skipping something here. Let's see. Oh, electric field lines. 18.7 is the electric field lines. Electric field lines. 18.8 is the electric field inside a conductor. 18.9 is the Gauss's law. Okay, so the Gauss's law will allow us to calculate the electric field due to different charge distributions. Okay, so here you go. We covered that. Charged object, the electric force, conductors, and insulators. We skip the other one, but you already have an idea what 18.4 is all about. The electric field, Coulomb's E-field law, right? Coulomb's law applied to the electric field. Electric field line was covered. Everything that's in boldface is what we covered in the book. And we still have to cover Gauss's law. Okay. And it is. And what else did I mention to you before? Okay. I mentioned to you that there are all sorts of important geometries, important charge distributions that we can calculate their electric field. The first one that I didn't mention to you, I'm going to put there at the top, okay, is the planar charge distribution. Let's put here at the top because it's the most important one. Is the one we will use in the first lab. Okay. So think about a plane. Flat plane can be a sheet, right? That we manage to electrically charge it. All those distributions here, they are uniform distributions, okay? The geometry is much more different. Okay, let me erase that. We will concentrate our study in the following charge distribution geometries. Charge distribution geometry. The first one is the most important one, the planar charge distribution. Very large plane that electrically charged, uniformly charged, and what type of electric field does it generate, right? But there is this other one that's very simple to calculate. It's the ring distribution, annular charge distribution. Okay, it's a ring also with an electric charge uniformly distributed. We have the case of a linear charge distribution, right? Here you go. Here's my pen. My pen is an example of a linear charge distribution. Suppose I can electrically charge this pen uniformly throughout its length. Okay. We have the circular charge distribution, which is a special case of the planar charge distribution. Can you picture that? We have the spherical charge distribution. It's just a sphere, uniformly charged, cylindrical charge distribution, and so on. Those are the ones that we can easily calculate using Gauss's law. Okay, and like I said before, lab number 1 deals with this type of charge distribution here, planar charge distribution. And let's talk about this one. Okay, and then we go back to the other. Here you go. That's my planar charge distribution seen sideways, right? My planar charge distribution, if we look from the top, or if you look from the right side or from the left side, it's going to look like that. This planar charge distribution in this special case is a positively charged distribution. Okay. As we already covered, you already know that positive charges are sources of electric fields. Okay, and what do I mean by sources of electric field? It means that the electric fields start at the positive charge, right? And that's what my drawing is all about. The electric fields start points from the positive charge away from the positive charge to another place in the three-dimensional space. It points away from the positive charge. But there is one more important characteristic of this planar charge distribution. There's one more important characteristic of this planar charge distribution. And I want you to memorize that. If your plane is very large, okay, and very large, I mean very large with respect to the points in the space, okay? So let's say this point right in here along with respect to the planar charge distribution, the distance of those points here to the plane is very small compared to the size of the plane, okay? So that's what I mean by a very large planar charge distribution, the distance from the plane itself. At this point here, this distance too is very small compared to the size of the plane. For this type of condition, whenever the plane is very large, the planar charge distribution is very large, the electric field ends up being uniform throughout the whole space. Okay, and that is the representation of a uniform electric field. And what uniform electric field means, right? Uniform electric field means that they are very well behaved. The electric field vectors are parallel to each other, and not just parallel, but they have the same intensity throughout the entire three-dimensional space. Can you remember that? We're going to write it down, and we can calculate that mathematically using Gauss's law. But at this point in time, I want you just to remember this specific characteristic of a planar charge distribution. Just want you to memorize this important characteristic of a planar charge distribution. And it is exactly this type of charge distribution that are going to work during the lab number 1, okay? Okay, so again, this is my plane seen sideways. This is the plane seen on the other direction, in the other direction, right? From the right or from the side. If you look here from the right side or from the left side, that's how exactly what you see. Okay, a bunch of positive charges very close to each other. If we have a negative plate, okay, we're still a negative planar charge distribution, we are going to have a similar electric field distribution. The only difference is that the electric fields are going to point towards the negative charge, not away from the charge, but towards the charge, right? Electric fields start at the positive charge and end at the negative charge. Let's write that down so I don't overwhelm you with this information, right? It's much better if you start writing down everything. Planar charge distribution. planar charge distribution. Okay? This distribution. This is the most important geometrical charge distribution. All right? And what else did I say? Let's take a look here. Oh, okay. Is the most important continuous charge distribution. That's the word that I wanted, that the expression was looking for, right? It is the most important continuous charge distribution. It's the most important geometry, right? It's the most important geometry of a continuous charge distribution. But make no mistake, right? The most important charge distribution is the point charge. The most important charge distribution is the point charge. That's the most important charge distribution because it is closely related to that law that we mentioned, right? Closely, it defines the Coulomb's law. Okay? And then among a continuous charge distribution, the most important continuous charge distribution is the planar charge distribution. The most important geometry of continuous charge distribution is the planar charge distribution. Okay, the planar charge distribution. Don't forget, we are talking about uniform planar. Let's put it planar. Let's put it this way. Instead of just planar charge distribution, let's write that down like planar uniform charge distribution, right? So now you know that the charges are uniformly distributed throughout the plane, right? And what do I mean by uniform charge distribution? I mean the following. It means that amount of charge here in this square that I'm drawing right here. Let me draw a square here. The amount of charge that we have in this square here. And I'm going to make it, let's see here. I'm going to do format. No, it's not format shape. It's going to be format shape, size, position. Is that the one? No, that's not the one. I want to make my square transparent. There's a way to do that in PowerPoint. I'm trying to remember how to do that. Translate that size and position. That's size and position. Maybe it's format shape. Let's see this format shape. Must be the few. Yeah, transparent. Okay. Here you go. I'm making my square transparent, right? If you go ahead, count the number of charges in this square, right? Let's make 100% transparent. Yeah, no. Let's make, yeah, 52% transparent is good, okay? The amount of charge in this square is going to be equal to the amount of charges in this other square. That's what a uniform charge distribution is, okay? You get a small square in this planar distribution, you know, anywhere this small square is located has the same charge, that has the same amount of charge. Okay, that's what a uniform charge distribution is. The number of charges anywhere is the same. Now, when I illustrate a non-uniform charge distribution, right? Let's write that down. Uniform charge distribution. Uniform charge distribution. We're not going to deal with non-uniform charge distribution, but I want you to understand the distinction between the uniform and non-uniform, okay? Uniform charge distribution. Now, what would be a non-uniform charge distribution? I'm going to illustrate a non-uniform charge distribution. Would be something like the following. You know, here you go. I'm going to eliminate some of the charges here. Oh, what happened here? It did something that I didn't want it to do. Okay. Why is it doing that? I think I know. Okay. I think I know why it's doing that. I'm going to put, yeah. Now, yeah, I'm going to put a return here. There are some tricks, right? Even to do something so simple in PowerPoint, there are some little tricks that we have to do, okay? See, do you see what I'm doing? I'm putting a return here. So I separate one row of electric charge distribution from another row. And when I finish that, I will be able to draw a non-uniform charge distribution for you. Okay, now let's see. See what I'm doing here? What am I saying here? I'm saying here that at this edge, the amount of charge is less in a given square is less than the amount of charge anywhere else. That is a non-uniform charge distribution is. Yeah, here you go. That's how we represent a non-uniform charge distribution. And now I'm going to already have like 3 of those. Here you go. My life becomes easier, right? Here you go. I want to, here you go. Let's see, and then I'm gonna copy all this row, and I'm gonna paste here. Now let's say, you know, the amount of charge increases from the edge to the center, right? Here you go. I am representing a non-uniform charge distribution. Okay, did you get the idea now? So the same square that you see here has, let's say, 1, 2, 3, 4. 4 times 2, 8 positive charges, right? Now, if you move that same square elsewhere, right in here, for instance, you're not going to have 8 charges. You're going to have only 3 charges. That's how we illustrate a non-uniform charge distribution. I can't go further than that, but I guess you got the idea now, right? What the difference of a uniform and non-uniform charge distribution. So if I want to make this uniform charge distribution symmetric, non-uniform charge distribution symmetric, right? All I have to do is to copy the top of the charge distribution and paste here at the bottom. Copy this other one. Let me finish this one. Uh-oh. you go. Why is it doing that? Okay, making my life hard here. Yeah, and now I'm gonna copy this one here, and I'm gonna paste down there. In this case, this non-uniform charge distribution has a symmetry. There's a symmetry. Here you go. See that? The amount of charge here at the top is exactly the same as the amount of charge here at the bottom. Here too, in this row. Okay? So there is a symmetry in this charge distribution. So throughout this course, we'll be dealing just with uniform charge distribution, like this one. It's the easiest one to calculate. One is trying to come in. Here you go. Now, so let's go back to the most important charge distribution is the point charge. Okay, it defines the Coulomb's law, and from the point charge, from the electric field, of a point charge distribution, we can calculate the electric field, the field of any charge distribution. Right? Now, after point charge distribution, in addition, right? In addition to point charge distribution, we also have a continuous charge distribution. The most important continuous charge distribution is the planar uniform charge distribution. To a point charge distribution, comma, this planar charge distribution is the most important charge distribution. Okay, don't forget the planar uniform charge distribution, right? The planar uniform charge distribution has an electric field distribution, that is also uniform, right? So don't forget that we have the concept of uniform charge distribution, right? And the concept of uniform field distribution. One thing is different from the other. Okay, don't forget that. And don't mix up one with the other. Here you go. Another student come in. And you already saw how does the uniform field distribution look like? How does a uniform field distribution looks like, right? It looks like several vectors with the same length pointing in the same direction. Okay? That's how uniform field distribution looks like. And I already showed that to you. Go back here, right? Here you go. That's how a uniform field distribution. But very important, the field is uniform just in one side of the plate, right? Either here or here, right? No, see, that the field is uniform just either in the left side or the right side. If you're going to say, is the field distribution uniform here in this region? No, in this region it wouldn't be uniform, because on the left side the field is pointing to the left, on the right side the field is pointing to the right. Okay? And the qualitative way of understanding this distribution is just the same way that we did before. Okay? You just look, for instance, let's see if I have a slide to explain that to you here. Doesn't look like I do. I'll have to do it. Oh yeah, I do have it right in here. Okay? So here you go. How do you, one way to obtain qualitatively, right, that uniform field distribution in a qualitative way is just to account for the electric field due to every small charge distribution in this plate, okay? So let's say this small charge distribution right in here at the very edge of the plate is generating, I'm going to ungroup. Yeah, let me ungroup here. Is generating this vector, this electric vector field, okay? Can you see that? Because this small charge distribution is further away from the other ones, the electric field, its electric field is gonna be weaker. Okay? And here at the center, what do we have here at the center? At the center we have the center of the plate has this electric field contribution right here. I'm going to ungroup it. Okay? This central charge is contributing this electric field. And all the other charges that are outside the center will be contributing an electric field that will have an angle and a shorter length, okay? When you sum all those vectors right in here, what do you end up having at the very center of this line? You're going to end up having this field, this net field distribution here. Do you see that? Right? You're just summing up vectorially all those vectors. The vertical component of those fields are going to cancel out with the field of the other one, but not the horizontal. If you keep on doing, not just for the central point, but for points that are close to the edge like this one, little by little, the field starts to deviate from that of a uniform field, little by little, okay? Just by doing this procedure, okay? The charge at the very edge here is going to contribute a field that's going to be pointing in the horizontal direction. This other charge is going to contribute a field that's going to point in an angle, and so on, right? And this other charge here, nearby the center is going to contribute a field like that. Okay? If you do that for all the points in the plate, you get a field contribution somewhat like that. Close to the central region, the field is very close to that of a uniform field distribution. Okay? And when you do the math, you learn that those fields that deviate very slightly from that of a uniform when you do the actual mathematical calculation. Okay? That's why the plate must be a very large plate, in size, right? In terms of size. So here you go. If Okay. If the planar distribution of charges is very large compared to the distance from the plane, comma, the electric field distribution will be very close to that of a uniform field distribution. Okay? Keep that in mind. What else you have to know? Right? What else you have to know? Those same ideas apply to the negative, to the negatively charged plate. Those same ideas. Same ideas, okay? Right here. Now, what else you have to know? What else you have to know? In the experiment, we are not going to do an experiment in which you have just a single planar charge distribution. In the experiment that we are going to do, and in real life too, what do? We generate a uniform. Here you go. Can you hear me now? We were momentarily offline, right? That's very
Yes.
Yes, can hear you.
Yes.
good. But we're back here. Okay, so let me start sharing the screen again. Okay, so I'm gonna write that down there in the notes. A positive, a planar charge distribution, planar uniform, uniform charge distribution that is positively charged, comma, generates a uniform field that points away from it. The field at the left of the planar distribution. The field points to the left, at the right, at the left side. One. At the left side of the planar distribution, the field points to the left. At the right side of the planar distribution, the fields point to the right. Okay. And now we're going to copy that and write down what happens when the planar charge distribution is negatively charged, right? Negatively charged. Towards it, towards the plane, okay? Towards the plane. Here you go. Points away from the plane. Here you go. At the left side of the planar charge of the planar distribution, the fields point to the right. And at the right side of the planar distribution, the fields points to the left. Okay? So here you go. What I wrote there is just the same here. This and this. Okay? Note, see this, what I showed to you here is just to say that the charges are negative, okay? Sigma here is related to the charge, to the sign of the charge. And now, what happens if we combine those two charge distributions, okay? What happens whenever we combine those two charge? When you combine those two charge distributions, something interesting happens. And that's what I'm doing right in here. I get my positively charged plane and put it close by my negatively charged plane. Okay? What's going to happen? Okay, the fields are going to superimpose, okay, each other. So here you go. I'm going to do for this, for the positive charge one only, okay? So here you go. This is going to be, hopefully it's not gonna take too long for me to do that. Oops, not this one. What you see right in here, are just the contribution to the electric field of the positive plate, okay? Of the positive plate. Let's see how I can do that. Good. So there's an easier way. Yeah, oh my God, I don't want that. Let's see. Yeah, good. It worked. It worked the way I want. It's just this one that now. Okay, so here you go. That's the contribution of the positive charge distribution only. That's the contribution of the electric field of the positive charge distribution only. Here you go. And then we can draw the contributions of the negative charges, negative plate only, right? Let's see if I can. You know what I'm gonna do? I'm gonna make it easy. This one here, I'm gonna change the color to red, right? And then I'm going to change their direction. Let's see if I can get that. No. Format object. Yeah, here you go. I'm gonna change their direction. Okay. All those arrows are going to be red as well, right? And this one here is gonna change direction, just like the other. Those are the contributions, the electric field contributions of the negative plate only. This one here, I want, yeah, here. No, that's not what I want. I want this one. Yeah, good. Now, you sum this electric field distribution to this other electric field distribution. What do you like? What are you gonna get? You're going to get a superposition that's going to enforce the field within the volume of the two plates, and you're going to get a field distribution that's going to cancel out in that volume outside the plate. Can you see that? Step by step. We are finding that out just by starting from the idea that each plate separately produces a uniform field distribution. In the next one, what are we going to do? We're going to sum those vectors, right? Here on the outside, the electric field is going to be approximately zero. but the field here on the inside is going to be very strong, twice as strong if you had just one plate. Here you go. That's the vectorial representation of the electric field. And that's the line representation, the electric field line representation of the electric field. Do you see the spacing between the lines? They are uniform, they are exactly the same, right? We can continue with this. I didn't do that. Let's see here. Yeah, here you go. They are not aligned, huh? What a shame. Okay. I can remove those that are not aligned so you can have a better idea. Okay, here you go. Did you get the idea? And I can do the same here at the top. Okay, I can do the same here at the top. That's the electric field line. And now we can write down what will be obtained here. When we place one plate next, one negatively charged plate next to the positively charged plate, both of them have the same density charge distribution, with the except of the sign. I use the section of the sign, comma. Then we obtain an electric field distribution that is uniform within the volume between the two plates, okay, and zero. An electric field that is, we don't need distribution here, that is uniform within the volume between the two plates, and zero in the volume outside the two plates. Okay. Going back here. So here you go. Let me copy that, right? I'm not gonna copy everything because it becomes too large in the snipping tool. Let's get my snipping tool here. Here you go. Copy only, right? So a planar distribution chart, uniform generates, right? A planar is positively charged. Okay, so I'm going to paste right here. Okay, and then the other one, a planar charge that's negatively charged here. One positively charged, right? Away generates points towards, and then We are going to get the other one here. We're almost at the point where we are going to take our break, right? Copy. Only. Here you go. It goes right in here. Center. We're going to shrink this one to save on space. Here you go. Like that. And then now we get this one here. Gonna look like that. Right? E field outside the zero. If we illustrate that in terms of electric field lines, it's going to look just like that. And don't forget, electric field lines are much easier to draw compared to the vector field lines, the vector fields. Much less work. Vector fields, vector field representation. Line field representation. Line field representation. We can make a little bit larger. Yeah. So I'm gonna take attendance again. This one's gonna be the last time I'm gonna take attendance. Today is, I didn't, interesting. Looks like I didn't take attendance on the 16th. Oh, the 16th was holiday. Here you go. That was a holiday. Yeah. Okay, Mirage, are you there?
Yes, Professor, I'm right here.
Let's see, Steve, I'm here. Okay. Susan Acosta.
I'm here.
Thank you, Susan. Mikara Alkema. Are you there, Mikara? Let's see here, Mikara. No, Mikara is not here. Okay, Ryan, are you there? Yeah, Ryan's not there either. Evelyn? I don't see Evelyn. Let's see, let's put, no, I'm gonna do the following. Most of you are present, right? So let's put one for everybody, and then I'll fix the rest. Okay, so Christina, are you there?
I'm here.
Thank you, Christina. Next, Ben Bandoy, are you there? Okay, thank you, Ben. Next, Queen Castaneda, are you there?
Here.
Thank you. Next, Emily Serna, are you there?
Here.
Thank you, Emily. Next, Isabella Cisnero. I don't see Isabella. Let's see. Evelyn is trying to come in. Luis Diego Cruz.
I'm here.
Thank you, Luis. Next, Delisha. I don't see Delisha. Gabriela Edwards.
Here.
Thank you, Gabriela. Next is Princess.
Here.
Thank you. Carlo Gallardo.
Here.
Thank you. Trin Hernandez.
I'm here, Professor.
Thank you. Next is Stephen Steven already. Okay, let me send me a message, right? Jeremy Landis. Are you there? Jeremy seems to be here. Thank you, Jeremy. Next is Paola Leones. Thank you, Paola. Thank you. Next, Pedro Lopez.
Here, Professor.
Thank you, Pedro. Next is Janie Maldonado.
I'm here.
Thank you, Janie. Next is Noemi Martinez. Thank you, Noemi. Isabel Medina.
Here.
Thank you, Isabel. Kimberly Morales.
Present.
Okay, thank you, Kimberly. Next is Ramon Dolores. Ramon Dolores Mora. I don't see Ramon here. Okay, so next is Arian Navidius.
I'm here.
Thank you. Next is Oni.
Here.
Thank you. Mario Ochoa.
You're welcome.
Mario Ochoa doesn't look like Mario is here, right? Okay. Next is Ahmad Olumi. Ahmad, I don't see Ahmad here. Arwa Paris.
I'm here.
Thank you. Next is Catherine Perez. Catherine is K, right? I don't see Catherine here. No, Catherine is C. Okay, yeah, I don't see Catherine here. Next, Nadia Cynthia Prum.
Here.
Thank you. Next, Tatiana Saldivar. Let's see, Tatiana. No, Tatiana is not here. Stevie Sanchez. Okay, Steve is here. Okay, thank you, Steve. Next is Jason Cervellon.
Here.
Thank you, Jason.
Mm-hmm.
Next, Francesca Sorrentino. I don't see Francesca. Chris Chenkertanian. Chris. I don't see Chris. Okay. Next is Dana Terry. Okay, so it looks like Dana is here, right? Yeah, Dana is here. Thank you, Dana. Next, Audrey Tylery.
Here.
Thank you. Next is Juan Torres Arellano. Thank you, Juan. And was everybody called, by the way? If you're not called, let me know. We have 28 students that answered. Looks like someone left, right? Let's see. There is an Evelyn. Are you there, Evelyn? Okay. Okay, doesn't look like Evelyn here. Okay, so let's have our break right now. Break. Let's see, 3:45. no, it's not 3, sorry, 11, right? 47. 10:48. Oh, here you go. 10:48 a.m. to 11:03 a.m. No, it's not 11:03. 28, 28, 68. Yeah, 11:03. That's right. So I see you in 15 minutes. Stop sharing. Back here. And oh, here you go. So now you should understand, you should know that two parallel plates produce a uniform field inside the volume of the two plates, in between the two plates, and electric field equal to 0 outside this volume. Okay. And what I want to do now, I'm gonna go back to this idea of the electric field. Let's see. And what I want to do, I want to talk about, okay, we're going to skip Gauss's law for now. Gauss's law for now. And we are going to talk about the electric potential, okay? We're going to talk about the electric potential here, electric potential 1. And then we're gonna go back, okay? Skip Gauss's law for now and start talking about the electric potential. While we're doing that, that's chapter 19. We're doing that because we need that for the lab. Then we go back to the electric field, okay? Then we go back to the electric field. The idea of electric potential is related to the idea of electric potential energy, which parallels the idea of gravitational potential energy we saw in physics 06, okay? So that's so let's start. Let us start with the electric potential energy. Right? In physics 6, we saw the gravitational potential energy. We saw the following we saw two types. Here you go. Two types of gravitational potential energy. Gravitational potential energy. One, the gravitational potential energy of a mass nearby the surface of the Earth, right? And in this case, remember what was the gravitational potential energy? In this case, we put down as U being mgy. Remember that? And we also saw the gravitational potential or energy of a mass at any distance from the center of the Earth. From the center of the Earth. In this case, the equation was different. The equation, do you remember what the equation was? We didn't derive it, but I displayed its equation. Well, I need an equation here. What was that? Oh, I hate that. Yeah, here you go. Let's see if we can. Yeah, good. U equal to what? Was big G, the mass of the Earth divided by this distance from the center of the Earth. Do you remember that? Did I erase it? Let me put in the line below. It'll be better. Here you go. Center, justify. Okay. Okay, U. Okay, now we have it. U is big G, big M divided by R. And we must have a negative sign here, right? Yeah, we must have a negative sign there. We did derive that. This one here we derived, but this one I just told you what was the relationship because we cannot derive, we cannot prove that mathematically with only algebra. We have to use calculus, differential calculus and integral calculus. The idea that we have for gravitational potential energy, the idea that we have for the electric potential energy parallels that of the idea of the gravitational potential energy, okay? And the potential energy is defined as, recall that the definition of potential energy is minus the work done by a special type of force. Do you remember that? What's the name of that special type of force? By a, let's see, a special type of force. Right? There is contact force and non-contact force, but then there's another way of classifying the forces here. There's another way of classifying the forces as well. Okay, special type of force that we call the conservative force. Okay? Recall that the definition of potential is minus the work done by a conservative force. Not every force is a conservative force. Also, recall that not every force is a conservative force. The force of gravity, examples of conservative force, right? Let's see, examples of conservative force. Here you go. We saw in physics 6 that the force of gravity nearby the surface of the Earth. Okay? The force of gravity nearby the surface of the Earth is given by mg. That's a conservative force. Another conservative force, the force of gravity at any distance from the center of the Earth. And that force of gravity is given by, I'm going to copy that and paste here. F equal to over r squared. And then there is one more type of force that is also conservative. It happens, okay, that the electric force is also a conservative force. It happens that the electric force is also a conservative one, is also a conservative force. Remember that the electric force has a similar equation, a similar relation compared to that the force of universal gravitational force. What's going on here? Yeah, let's skip this way. Good. The electric force is given by K, Q1, Q2, right? Divided by R squared. And we can take the sign off here. Because if one of those two charges is negative and the other is positive, the force is going to be attractive. Okay. Oh, the other one, I gotta list another one here. The elastic force is also a conservative force. And the elastic force is K minus Kx. So 4 examples of conservative forces. Okay?